gx omega t over x plus b is perpendicular to omega, right? So in order to show this, prove this, you need to just get any 2 points on the hyperplane. So let's say x1 and x2 are any points on the hyperplane, okay? And sorry for my bad handwriting, so if you have any questions regarding my handwriting, please tell me. So if x1 and x2 are any points on the hyperplane, then we can write the equation like gx1 is equal to omega t x1 plus b, and g of x2 is omega t x2 plus b. Now we have these two equations, and using these two equations, you can write g over x1 minus g over x2 is equal to omega t over x1 plus b minus omega t over x2 minus b. So this b goes off, and you can write this as omega t is x1 minus x2, okay? So this means that since we know that x1 and x2 are any points, and x1 and x2 are any points in this hyperplane, we can show that since this is like, you said this is equal to 0, right? Okay. So we can write this as a 0. So we are shown that omega and any 2 points or any points on the hyperplane is perpendicular to omega. So this shows everything that what we need to show. The hyperplane is perpendicular to omega. Okay? So any questions regarding problem number 2? No, then, okay. So let's read here. So problem number 5. So in this problem, we want to explore reflection transformation, and this is just a mirror of x, so that we can produce a mirror vector z with respect to vector v. So we want to first find out whether the reflection transformation is linear or not. So for some kind of transformation to be linear, that needs 2 requirements. First, superposition, right? So what is superposition? Okay. The concept of superposition is just x1 plus x2. This t here is just transformation. It's equal to tx1 plus t to the x2. So we're going to find out whether this kind of equation satisfies for reflection. Okay? So we're going to use just simple geometry or geometric ways to find out whether this equation is true or not. So for example, if there's a v here and there's an x1 here, then the mirror of x1 is equal to z1, right? So basically the t of x1 is equal to z1, okay? And also if x2 vector is defined as like this, then x2 mirroring the x2 vector will give us z2 vector, which is like this, okay? So t to the x2 will be z2. So we want to find out whether this equation satisfies or not, right? So we're going to define a new vector called like x1 plus x2. Not new, but just adding 2 vectors, x1 and x2. Okay. And there's the mirror of the x1 plus x2 vector is also addition of these 2 vectors, right? So with this simple geometry, we can find out that t of x1 plus x2, so mirroring the x1 plus x2 vector is equal to z1 plus z2, right? z1 vector plus z2. Okay? Since we know that tx1 is z1 and tx2 is z2, we can write tx1 plus tx2, right? So we find out the superposition workout, right? So second thing you need to satisfy so that the transformation can be a linear is homogeneity. So what is homogeneity? So homogeneity is defined as T over kx is equal to k over tx, okay? So we need to find out whether this equation is satisfying for the reflection or not, right? So also, like with the geometric, so geometry, this is x, and let's say that this vector is equal to like kx, okay? And the reflection of x is of course z. However, reflection of kx is also kz, right? So we find out that T over kx is equal to kz, okay? And we know that the reflection of x is z, right? So k over tx. So we find out the homogeneity also satisfied. So we can say that since these two conditions are agreed, so we can say that reflection transformation is linear. So the second problem says that if yes, linear, find matrix M such that Z is equal to MX. So this is quite tricky part, but in the lecture note there is a very simple solution to this this question. So so we want to find out some matrix M so that this kind of equation is satisfied, okay? So in the lecture note, there's like a V vector here, and there's a X vector here. And we can define omega vector, which is projection of X vector on the direction of V, okay? So projection of X vector on the direction of V, okay? So this is omega vector, okay? So, and also we know that the Z vector is supposed to be like this, right? So first we're going to decide what is omega vector, okay? According to the equation that is on the lecture note, it says omega is equal to px, and p is just a projection of x, okay? So is equal to vt x and vt v and v, okay? And this equation can be changed to v vt and vtv. So if you don't know why this equation is satisfied, then go back to the lecture note and you can check it out there. So so we now find out what is the projection, which is omega, projection of x on the direction of v. So we find out omega. So why is the omega important? Because we can find that we can make expression of z vector with this omega nx, okay? So if we go on 2 omega, like this vector is 2 omega vector, okay? This vector. And then go back to the negative x, okay? Then we have z vector. So this means that z vector can be shown as 2 omega minus x, right? So you're going 2 omega and go reverse to the x, right? Go x, then we add z, okay? So since we can write this equation like this, we know what is omega in terms of x, so we can just write 2 over vt and vtv x minus x, okay? And this is equal to we want to find out the matrix M, right? So we can just write it. Like this, okay? So this is the matrix M that we want to find out, okay? So this is I here. So we have find out what the matrix M is, and the last things is, so we are given the V vector, and we need to compute the M, matrix M, and its eigenvalues and eigenvectors. So we know the equation M, just use a V vector that is given in the problem. We know the equation for M vector, right? So we're gonna just use the V vector that is given in the problem, okay? Okay, and this gives us like 2 times 2 over 1, 1, 1, 1 minus 0. And this, so this is just simple matrix calculation, so I'm going to skip the explanation. So now we have the M matrix, so we want to find out its eigenvalues and eigenvectors. So in order to compute the eigenvalues and eigenvectors, we're going to have to use a simple equation, mx is equal to lambda x, okay? So m minus lambda I over x is equal to 0. So you need to find out the eigenvalues that we want to get for this problem. You're going to use determinant of minus lambda 1 minus lambda is equal to 0. So M was this matrix, right? And minus lambda I gives us this equation. Okay, so let's find out the eigenvalues. So this gives us lambda squared minus 1 is equal to 0. So we have 2 eigenvalues. Lambda is plus minus 1. Okay, and then we're going to find the eigenvectors for each eigenvalues. For lambda that is equal to 1, we have eigenvector of 1 over 1, okay? And for lambda that is equal to minus 1, we have x1 is equal to like minus 1 or 1, okay? Right? Yeah. So this eigenvalues, 2 eigenvalues and 2 eigenvectors was the answer for this question. Also, there can be other forms of eigenvectors, so it doesn't matter if your eigenvectors are different from this answer, okay? Now, let's go to problem 6. So problem 6 is just telling us the definition of projection, and we want to find out the given matrix P is a projection or not. So first, in order to satisfy the projection condition, this kind of equation needs to be satisfied. So P squared is equal to P, okay? So this is simple, right? P squared, since the P vector is given, the P matrix is given, right? This gives us 0, 1, 0, 1, which is equal to P. So we find out the given P matrix is the projection, okay? So after we have the P, we just found out the P is a projection. We need to draw a sketch from the vectors and their images under the map P, okay? So simple, the projection of vector 1, 2 first. And this gives us 0, 1, 0, 1, 1, 2, this gives us 2, 2 vector, okay, 2 by 2 vector, and this gives us 0, 0 vector, and the last is a 3 by 3, okay? So let's sketch these vectors in the plane. So original point was 1 over 2, okay, right here. And this point goes to the 2 by 2 with the projection vector, matrix 2, okay? And the original point was nearly 1, 0, like here maybe, okay? And this point goes into the 0, 0, so like this point. And last 0, 3 here goes into 3 by 3, So basically, you can say that this line is just y is equal to x. So the P projection is actually a projection of points on the y is equal to x line, okay? So let's go on to 6b. So there's a new matrix Q, which is Q is equal to I minus P, okay? So I minus P gives us, the P vector was this vector, right? So this gives us a new matrix, 1 minus 1, 0, 0, okay? Okay. So we want to first find out whether this Q is a projection matrix or not, and also we want to find out what is the projection of these 3 points with respect to this Q projection, okay? So let's first find out whether Q squared is equal to Q. So simple, right? 1 minus 1, 0, 0. 1 minus 1, 0, 0. So this gives us 1, negative 1, 0, 0, okay? So this satisfies the equation. Q squared is equal to Q. So now we find out that the Q is a projection. We want to find out the projection of the 3 points with respect to Q goes on to, okay? So it's basically the same step. So Q, 1, 2. So since this is just a simple matrix computation, I'm not going to explain details about it, okay? So let's draw these points on the same plane that we did for the P. So the original point was 1 over 2 here. And this points with the Q projection goes on to minus negative 1, 0. So this is negative 1. Goes like this, and the second one it just stays same, okay? Does not change anything. And the last one, 0,3. So this point, 3 here, goes on to negative 3,0, okay? Like this, okay? So this is the end of problem 6. So next problem is problem 8. So this problem is quite simple if you have watched carefully about the lecture notes. So let V is a unit vector and Px is the orthogonal projection of x on the direction of V. So what is x? That is that x CV for some real constant c, then Px is equal to x. And if x is perpendicular to V, then Px is equal to 0. So we have done this similar question in the problem 5, I think. So for the question 8. So the question basically asking is, here is x vector, and we want projection, there is a v vector, right? And the projection of x on the direction of v is the omega that we discussed before, okay? Okay. Now we have omega, and this omega can be written like omega is equal to px, and p is a projection that we want to find out for this question, right? If you go back to problem 5 and look at the equation again, then we can write this as vtx of a vtv v, and this equation is equal to vvt over vtv x, okay? So with this concept, we can now see that p is just equal to this, okay? But since we know that v is a unit vector which have size of 1, so we can just write this is equal to 1, right? Then vt, okay? How simple. So this question is quite simple if you have watched the lectures carefully. So basically the projection concept is same as in the problem number 5. But since v is a unit vector, the bottom term goes into 1. So we can just prove that p is equal to vvt, okay? So next question is problem 11. 11 says, let A be an invertible matrix with eigenvalues of lambda 1 to k, and corresponding eigenvectors are v1 to vk. So what can you say about the eigenvalues and eigenvectors of A to the inverse? Okay, so the inverse of A, right? We want to find out the eigenvalues and eigenvectors of inverse of A, right? So when we want to compute the eigenvalues, we used to write AV, which is V is an eigenvector, right? Is equal to lambda of V, okay? So this is like eigenvectors and this is eigenvalues. AV is equal to lambda V, okay? So if we multiply the inverse matrix A to the negative 1 in the front of these two equations is one equation, okay? Then we can get this kind of formula. And since we know that A of inverse times A is just I, you can write V is equal to A to the negative 1 lambda V, okay? And we know that lambda is just some constant, so we can just write A to the negative 1 V is equal to lambda 1 over lambda over V, okay? So this equation satisfies. As you can see in this equation, the eigenvectors of inverse of A is just same as the eigenvectors of A, okay? However, the eigenvalues are in opposite form, okay? So if A's eigenvalue was lambda 1 to lambda k, then A minus 1's eigenvalues will be lambda 1 over lambda to 1 over lambda k. And also the eigenvectors will be same because, as you can see, just nothing changed, right? So V1 to Vk. So this 2 was answer, okay? This is another simple problem, okay? So any questions? Okay. So the last question, problem 15. This problem can be really hard if you have not watched the lecture carefully, because there's a simple method to find out a solution for this problem. So in the page 60, I think, page 60 of your lecture notes, you can find out the least norm solution. The least norm solution is basically solving the optimization problem for any norm questions. This is like an L1 norm and subject to some kind of blah, blah, blah. So, I think I need to write this equation, okay? 2x1 minus x2. Okay, so we have constraints and we want to minimize the L1 norm of x, okay? So we want to find out, we want to show this equation in terms of matrix form, Ax is equal to B. So this is simple, right? A can be 2, -1, 1, -1, and 0, 1, -1, -1, okay? And x can be x1, x2, x3, and x4. And last, b can be 3, 1. So in the lecture note, page 60, there's a least norm solution, yeah? So basically, this least norm solution is easiest way to find out a solution for this minimization or optimization problem, okay? So the least norm solution is defined as So, since we know the matrix A here, and we know matrix B here, just simple matrix computation will give us answer, right? So I found out some of you just used Python to compute this dirty math, but I'm suggesting you to use your hands for this problem. So for the problems that you need to use the Python, I will inform you beforehand, and if there's no specific direction to use the Python, just solve it by your hand, please, okay? So for this time, I'm going to just let it go because I did not remind you. So let's compute this quite dirty matrix, okay? So X, optimal solution can be written as A of a transpose, right? Then we can write 2, -1, 1, -1, 0, 1, -1, -1. Times, there is A times A of a transpose. Of inverse 3, 1. So let's find out this first, okay? And this can be written as 2, 0, -1, 1, -1. The matrix in the middle goes into 7, right? -1, -1, 3 over inverse. And 3, 1. Since this is just simple 2 by 2 matrix, you can just simply get the inverse of this matrix, right? So the inverse of this matrix is okay. So I'm sure that you guys all know how to make the inverse of 2 by 2 matrix, so I'm not going to just go over that. So we know this matrix now, right? Then we're going to write this equation as so I'm just giving this constant, moving to the front of the matrix problem, okay? And this gives us okay. Again, this is just simple matrix computation. And this gives us 1, 0, 0, negative 1. So this is the optimal solution we got. And since we want to find out the L1 norm, so minimization of this, right? So you can just write it as 2. So some of you just finished your solution here, so it's fine, because just simply you have done all things. And also there can be another solution that is not equal to this, okay? So if you have used another method, not the least norm solution, and you used your own method and you got some answer, the different answer to this optimal solution is fine, okay? I'm gonna grade it. I'm not gonna just grade whether you have this answer or not, okay? I'm gonna look at your solution and whether you did it correctly or not, okay? Now we're gonna go over how to use the Colab, as I mentioned in the beginning of the class, okay? So if you go to a Colab, like type Colab here, and just click the link, you can just create a new note here. I'm not sure why this is Korean, but just click the new note. Then you will be able to see this page, okay? Which is same as this page in English. And so if you can see here, there is code and text. So if you click code, you can just add any another column, another line that you can write your codes at. And if you add a text, you can just write a text on it. So why do we need text? Because for homework problems, there will be like homework 5 will be for the handwritten problems, and like homework 6, like problem 6 can be coding problem. Then you need to write this problem. This specific problem is problem 6. Okay, and if you click Shift Enter at the same time, okay, or Shift and Enter at this column, then it just goes on to the next line, okay. And you can write your codes here, in this column. Okay. Okay. So this is just code section and text section. So don't forget to specify the problems that you are solving in the below codes. Okay. And next thing is how to mount Google Drive on this specific notebook environment. Okay. So click these files, and you'll be able to see some options, and after a few seconds. Okay, and here is a mount drive, right? Just click the mount drive, and it automatically mounts a Google Drive onto this environment, so that you can access files that is stored in the Google Drive. Okay, so there will be some homework problems that require you to download some files and upload to Google Drive so that you can use it on the Colab, okay? So now my drive is uploaded to this environment, right? So I'm gonna just show a brief example of how to code, how to like access this specific PostTech file, PostTech JPG file in the Colab environment. So this is just example code, so you need to know, okay? So if you're doing homework, you need to just use some libraries that have some good functions that can be used for your homework. But this is just an example. This is just showing an image. So that depends on your homework problem. So you need to find out what is satisfied. So I'm going to define the image path. So our image is in the PostTech JPG. So first, our drive, we need to go into the drive, right? So here, drive, and under the drive, there is a My Drive section, okay? If you mount the drive, Google Drive on this Colab, I'm pretty sure that the following drive and My Drive section will be same as mine, okay? And next, under the My Drive section, there is a PostTech JPG, right? Now I define the path to my file, right? So add codes, okay. Oops. Now I define the image. Yep. So I perfectly, clearly use my image path, which is here, to access my image file. So this is just a simple example. So if you upload your files or any data that will be used for your homework or midterm on a Google Drive, then you can use path to access this file. And while you're doing homework and you have problem with mounting the Google Drive on this kind of environment, then please email me so that I can tell you more details. So for the submission of your homework, you need to first change the titles of the notebook, of course. You can just submit the untitled 0 to homework, right? So you want to change homework 1, like blah, blah, blah. Okay. Next, you need to download this file so that you can submit on the PLMS, right? So you can just click File here and goes into Download and download IPYMB, okay? Then your file is downloaded and you can just submit this file onto the PLMS, okay? And then I'm requiring two things to do from this Colab. First, download this IPYMB file and upload it to PLMS. Second thing is to make a link so that I can see this Colab via internet or something. So use their share, okay? If you click this share, this gives me an option. This is restricted, right? You need to change this to anyone with the link so that I can see this homework that you have solved so that with my Chrome, right? Okay. So copy link here, and link is copied. And there is a PLMS. In the PLMS there is a short box where you can type yourselves. So just copy and paste the link on the section, okay? Like if you, so I have just copied the link, and if you paste the link to this site, then it actually leads to the notebook that you have wrote. Okay. So as I said again, you need to do two things: download the IPYNB file, and then create a share link and upload it to PLMS. So don't forget this access time, okay? Most students start with this restricted option, but I want you to change this to anyone with a link, okay? So you need to do both, not just one, okay? Both IPYNB and a sharing link. And I'm gonna tell details when you need to do after, I think in homework 2 or 3, okay? And then the next thing you need to do is how to use GPU on this Colab. You know, the GPU is much faster when you deal with the large data, right? So you need to use GPU in this Colab. You go into runtime. And the change runtime type, click the change runtime type, and there is a hardware accelerator. In this section, you can click the GPU, and since you're using free account, it will be standard. If you pay more, then it will change to Pro, but in this class, we don't require any accounts that use that kind of, a lot of GPU, so just press save. Okay, then your runtime is changed to GPU. So every codes will be run on a GPU, not CPU. So GPU is way faster in deep learning, but since we're dealing with machine learning only, it is like not that big difference on the using GPU and CPU. I'm just showing an example. Okay, so this GPU is limited for the free accounts, so maybe I think 4 hours of training will, your account will be blocked for a day after 4 hours using GPU. However, in this class, we don't require that much of a GPU, okay? So you don't need to worry about using free accounts on the Colab. So any problems or questions regarding using Colab? So you need to use from maybe homework 2, so this is very important. So if you have any questions about using Colab, you can send me an email. Okay. If there's no question, I'm gonna just solve a simple example problem that was in your problem set. So homework. This problem 14 was not homework, but I'm going to just solve it as an example. So this question is quite simple, right? Just there's a system of equation, and we want to write the equation in the matrix form AX is equal to B. However, this is quite important here, is you need to write codes, right? So I think it's your first time using the Colab. I'm going to show you. So problem 14, right? Problem 14, and add another text, A. Okay. Now, the problem was to write this equation in the form of AX is equal to B. So if you have done this problem by your hands, then you can just write simple answers like 83, 12, 10, 68, 84, 95, 32, 23, 43, X, Y, Z is good. Simple. So we want to write this simple equations or matrix form in the Colab, right? So in order to define a matrix, we're gonna use a special library that has a function that can define a matrix, which is called the NumPy. So NumPy is very often used in the Python, so you need to remember this. So import numpy as np, okay? So we're gonna import numpy libraries as np, okay? So name np is up to you, but numpy is important, okay? So we have now imported the library, and we're gonna define the A matrix as the problem required us. So this np dot matrix means we're gonna use a matrix function. Matrix function that is defined in the numpy, okay? And as you can see, this Colab tells us the parameters that we need to define, right? But I'm gonna just use here. So in order to define our matrix, you're gonna first use a square bracket so that any numbers in between the square brackets are in a matrix form. So in this Python, you need to define matrix in line by line, okay? So let's first define first line, which is this line, okay? So when you define a line, you will need to use another square bracket and just type 83, and 12, 10. Like 83, 12, 10. Now we have defined the first line, okay? The second line is defined after the comma of a square bracket, and you need to define another square bracket. And there's negative 68 here, 84, and 95. Okay? Now we have defined the second line, and the last third line starts 32, 23, and 43. Now we have defined a matrix, okay, line by line. This is very important. And now let's define matrix B. So as you can see in this matrix B, there is only a number in a line, okay? In that case, this is the same, okay? We're going to use the numpy matrix. Oh, sorry. It's basically same, 1 for 1. There's only one number, so you don't need to put comma inside of the square bracket for defining a line. And there's a 1 for 5, 89, okay? Now we have defined matrix A and B, okay? So let's go back to the question, problem B. So it asks, does this system of equation have a solution or not? So let's find the solution of the system of equation, which is AX is equal to B, right? So first, we need to find a solution for AX is equal to B. Okay? This can be simplified by multiplying inverse matrix in the front of two matrices. There's one B, okay? And this goes into I. So X is equal to A of inverse times B. Simple, right? So let's do this. A of inverse. So now we're doing the problem B, right? Problem B here. And then we need to write X, which is our solution if you have one, is A of a inverse, right? Times B. So basically, so basically this dot I means inverse of this matrix A that we defined before, and this B matrix is just the B matrix that we have used, okay? And we define this X, and we're gonna write print X. Now the solutions here, okay? Simple, right? So we found out that this question does have a solution, right? However, we want to let's assume that the problem itself is actually minimizing this ax minus b. So from the equation in the lecture notes, we're going to use the least norm square. Okay, just this is just for your example. So we know that we have a solution, but I'm going to just do the bottom problem, minimization of ax minus b. So also this is the norm question. So you need to just use the least norm solution in the lecture note. Okay, like problem 15. Then the x optimal solution is defined as a over inverse AT B. Okay? This was the solution. And we're going to just write this kind of equation on the Colab. So let's define another variable, like optimal solution is equal to same. A of a transpose is defined as A dot T, okay? Transpose, right? Times A, and inverse of this multiplication is just dot I, okay? Times A of a transpose, right? Times B. And then so you can see that optimal solution to minimize the ax minus b is same as the solution above, x, okay? So the system of equation have a unique solution of this. So this is, okay, so after you've done this, like let's assume that this is homework. As you can see in the file, download, IPYMV, and then what? And then share, goes into share. And copy the link, and please submit in the PLMS these two files, okay? When you're doing your homework. So from like homework 2, there will be some coding problems. So for coding problems, I'm gonna inform you that like problem 5 and 6 are coding problems, and problem 1 and 2 are like handwritten problems, okay? I'm gonna inform you before that. So as you can see in this problem set, there are many questions that were not given you as your homework. However, I'm strongly recommend you to solve this question by your own hand because it will be helpful for your midterm exam, okay? So some of the question might be similar to this question that you haven't solved before as your homework. And also there can be some problems in the homework problem that you can see on the midterm. So I'm strongly suggesting you to solve these problems that are not given as homework. And while you're solving these problems that there were no solution given to you, and you have stuck into some in the problem, then please email me so that I can tell you how to solve these problems. Okay?